Good afternoon, everyone. So I'm Sam Molius, and I work for a company called Trail of Bits. If you're not familiar with Trail of Bits, we specialize in high-end security software, and a large area of focus for us is blockchain. We try to apply real-world research to speed up our security reviews, and much of that research is turned into tools that we then open source. And open source tools of ours that you might have heard of or used include Slither, a static analyzer for Solidity, Echidna, an Ethereum smart contract fuzzer, Amarna, a static analyzer for Cairo smart contracts, and Tealer, a static analyzer for Algorand smart contracts. But in this talk, of course, we're going to talk about Solana. So in particular, I'm going to describe to you some lints that we have developed for Solana programs, and those lints were inspired by the sea-level attacks. And one runs those lints using Dylint. So in this talk, I'll describe the sea-level attacks. I'll say a little bit about Dylint and how it works. I'll then describe the lints themselves and then explain how you can try these lints on your own programs. So first, what are the sea-level attacks? So from their GitHub description, they are examples of common exploits unique to the Solana programming model and recommended idioms for avoiding these attacks using the Anchor framework. Now, I'm sure that many of you are familiar with the Anchor framework, but in case not, from its GitHub description, it is a framework for Solana's sea-level runtime, providing several convenient developer tools for writing smart contracts. Again, if you're not familiar with it, Anchor has both on-chain and off-chain components. By on-chain, I mean it consists of types, traits, macros, etc., to assist in writing Solana programs, and it also has off-chain components to assist in testing Solana programs. But for the purposes of this talk, we're mostly interested in the on-chain components. So the sea-level attacks are a set of programs whose purpose is to demonstrate proper use of the Anchor framework. Today, the repository consists of 11 examples. So each example has 3 versions, an insecure, a secure, and a recommended version. Roughly speaking, the insecure version is a program that exhibits some vulnerability. The secure version is a version of that program with the vulnerability mitigated in some way, but not necessarily the recommended way. And then the recommended version is, quote unquote, the idiomatic version of secure as encouraged by the Anchor framework. And this is according to Armani Ferrante, who, if you don't know, is the creator of the Anchor framework. So as I mentioned, there are currently 11 examples, and you can see them up here on the slide. So they range from things like ensuring that signers are properly checked, to ensuring that accounts are properly initialized, to ensuring that accounts are properly closed. But the one we're going to dive into a little bit in this talk is ensuring that owners are properly checked. Okay, so as I mentioned, each example has 3 versions, an insecure, a secure, and a recommended version. And what you see on the slide right now are the essential components of the insecure and the secure version. So what these programs do is they take an account which is expected to have been created by the SPL token program, they fetch a balance from that account, and then they log it. Now, why is the insecure version insecure? It is because it doesn't check context accounts token owner. That is, it doesn't verify that the passed-in account is actually owned by the token program. So in theory, the caller could have created the account moments before issuing the transaction and passed it into this function log message, and the insecure version of log message would happily accept that account, whereas the secure version would reject that account because it is not owned by the token program. Okay, now, if you're looking carefully, you may notice that there is this reference to an owner field here. And you may wonder, well, isn't that the owner check? Why is that not the owner check? And the answer is that this is subtle, but there are actually multiple notions of owner at play here. So what you see on the slide now is 2 structs. The struct on the left is Solana program account info. So this is the data that a Solana node associates with each account. And you'll notice it has an owner field. This is the one that we're interested in, because this owner field determines who gets to write to the account data, for example. Now, for the SPL token program, for some accounts that it manages, it interprets the data within those accounts to have this structure here. That is the structure of an SPL token state account. That struct has an owner field, And that field is checked by both the insecure and the secure versions of this program. However, that's not the one we're interested in for this example. The one we're interested in is this one, and that is the field that is not checked by the insecure example. OK, I just want to mention quickly that many of the details I just covered, one is largely left to figure those out on one's own, which is to say the C-level attacks documentation is somewhat light. Having said that, someone who goes by the handle of PencilFlip on Twitter wrote a really nice thread describing 10 of the 11 C-level attacks, and I highly recommend it as a resource for understanding these attacks. OK, so that's a little bit about the C-level attacks, so now I'm going to talk about Dylint. So Dylint is a tool for running Rust lints from dynamic libraries. So first, what do we mean by a lint? So the Wikipedia definition of a lint says the following. It is a static code analysis tool used to flag programming errors, bugs, stylistic errors, and suspicious constructs. If you've been programming in Rust for long, you've probably run into compiler lints such as unreachable code, unused imports, or wild true. So these are lints that are built into the Rust compiler. And if you regularly run Clippy on your projects, and I highly recommend that you do, then you've probably run into Clippy lints such as too many arguments, from over into, or redundant closure. These are examples of lints built into the Clippy linter. OK, so Dylint is similar to Clippy, but whereas Clippy runs a predetermined static set of lints, Dylint runs lints from dynamic libraries that the user names. And in this way, Dylint allows developers to maintain their own personal lint collections. So here's a little bit about how it works. So for reasons not terribly important to this talk, both Clippy and Dylint are divided into a cargo command and then what is called a driver. And intuitively, you can think of the driver as a wrapper around the Rust compiler. So when you run Clippy, for example, you invoke the cargo command, which in turn launches the driver. And then the driver says to the compiler, hey, when you run your own lints, would you please, in addition, run these lints that I have statically linked in? So Dylint is similar. You invoke the cargo command, which in turn launches the driver, which then loads one or more dynamic libraries. And then the driver says to the compiler, hey, when you run your own lints, would you please, in addition, run these lints that I have dynamically loaded? You can put as many lints as you want into a dynamic library. However, we have optimized for the case of putting one lint into a library. And the reason why I say this is we want to make it easy to get a lint up and running quickly. So we make it easy to package a single lint into a library. And for the case of a one-lint library, the structure of the lib.rs file will typically be like this. So there'll be an invocation of a declare lint macro, which by convention has a Rust.doc comment with some documentation about the lint. Then there's the lint name, the default lint level, which is nearly always worn, and then a short description, which appears if you ask Dylint to list the lints in the library. And then every lint will include an implementation of a lint pass trait. That implementation will include one or more check functions. And these check functions are concretely things like check expression, check statement, check block, what have you. And it's within those check functions where the actual analysis is done and the determination of whether or not a warning should be emitted. One point I want to leave you with before continuing is that while some packaging is necessary to put the lint into a library, by and large, writing a Dylint lint is essentially no different than writing a Clippy lint, is essentially no different than writing a Rust compiler lint. And what I mean by that is that the APIs that you use to do the actual linting are the same in each of the three cases. So Dylint doesn't force you to learn a Dylint-specific API. So for example, the late lint pass trait that you saw on the previous slide, that trait comes from the Rust compiler. It doesn't come from Dylint. OK, so as I mentioned, we have developed these lints which were inspired by the C-level attacks. And so here again are the C-level attacks. We currently have lints for 6 of them. For 2 of them, the lints are currently in development. For 3 of the C-level attacks, we have not yet been able to identify a lintable condition. And what I mean by this is we haven't been able to identify a feature that a program would have to exhibit that, if it did, meant the program was vulnerable to that C-level attack, and which feature we could identify programmatically. Having said that, if if this is a failure of imagination on our part and you have ideas, we'd be open to pull requests. But now, just as we went into the owner checks C-level attack in some detail, I'm going to go into the missing owner check lint in just enough detail to give you the flavor for what one of these lints looks like. OK, so as I mentioned, there's typically an invocation of a declare late lint macro. And so it will include a Rust.doc comment, with some documentation describing the lint. In this case, it's been slightly abbreviated. Then there is the lint name, the default lint level, and a description which appears if you ask Dylint to list the lints in the library. OK, and then as I mentioned, every lint includes an implementation of a lint pass object with one or more check functions. Now, before we get into too much detail, I just want to remind you what the vulnerability was in the insecure example. The vulnerability was that it made reference to a Solana program account info struct, but didn't check its owner field. So this is the lintable condition that we want to identify with this lint. And so the way this works is as follows. So this method, check function, this will get called by the Rust compiler for each function, method, or closure. Then this function, getReferenceAccount, is a function defined within the same lib.rs file. And what it does is it walks over each expression within the function body, and it identifies those which have type, Solana program, account info. It collects those all into a vector. Then, for each such expression identified, this function contains owner use is called. What this function does is it does a second traversal of the function body, and it looks for an expression of the form account expression.owner. So account expression is one of the expressions we just found in getReferencedAccounts, and this dot and owner are literal. If no such expression can be found, then a warning is issued. This account struct is used, but there is no check of its owner field. So by and large, we test the lints with the actual C-level attack code. In a couple cases, we have to make small modifications in order to get the code to compile. But by and large, we use the actual C-level attack code to test. And so if you run the lints on the insecure version of the owner check example, you get a warning like this, which should look familiar to you if you're used to seeing Rust compiler or Clippy lints. And what it's saying is it identified this expression here, which has type, Solana program, account info, and yet nowhere within the body in which this expression appeared could it find context accounts token owner. If you run the lint on the secure example, you get, as you'd expect, no warnings. Now, before closing, I want to make a quick point in regard to how our lints behave with respect to anchor programs specifically. And to do that, I'm going to make this point by saying a few words about the type cosplay C-level attack and the lint that we developed for it. So I won't go into the same level of detail, but here is the type cosplay vulnerability in a nutshell. So you have a program which does proper ownership checks, but operates on multiple types of accounts and doesn't have a way to distinguish among them. So here you see we have this update user function, which expects to receive a user account. However, it actually operates on multiple types of accounts, user and metadata. And if you notice, both contain a single public key. So we would expect these two accounts to serialize the same way. So the issue is that an attacker could pass in to update user a metadata account, and there is nothing to stop update user from operating on that metadata account as though it were a user account. So one way to mitigate this vulnerability is to add to each type of account that the function operates on a discriminant field. And what this field will do is it will hold one constant for one type of account. It'll hold a different constant for every other type of account. And so then the idea is that the program can check the value within this field in order to determine the type of account that it's operating on. So that's the vulnerability in a nutshell. Now, what you're looking at now is no longer the insecure and secure versions, but the insecure version and a slightly modified version that we have prepared for testing. So in this slightly modified version, what we have done is we have replaced this use of the derive macro with a use of the anchor account macro. Now, what does this macro do? Well, it does several things. In particular, it implements these traits for the struct that it annotates. And what I want to highlight here is the way that it implements serialization for that struct. So in particular, it reserves the first 8 bytes for a unique account discriminator. So more or less the fix I was just describing previously. Moreover, the way it implements anchor deserialize is such that this try deserialize function will check those 8 bytes. And if those 8 bytes are not the value that is expected for the account that you're trying to deserialize, it will raise an error. So if you run the lint on the insecure example, you get a warning like this. Type does not have a proper discriminant and may be indistinguishable when deserialized. However, if you run the lint on the insecure anchor example, which I just showed you, you instead get this warning. User type implements discriminator trait. If you are attempting to serialize here, you probably want to try deserialize. So in other words, what the lint is saying is, hey, I noticed that you derived the discriminator trait for this type user here, yet you're calling try from slice. And try from slice doesn't get you the benefit of having implemented that trait. So that's probably a mistake. Probably what you meant to do was call try deserialize. OK, so I would like to invite you to try these lints on your own code. Doing so is relatively easy. It's 3 steps. First, you're going to install 2 binaries from crates.io using the command cargo install cargo Dylint Dylint link. You're then going to add these lines to your project's cargo toml file, which tells Dylint where to obtain the lints that you want to run on your project. And then finally, you're going to run this command, cargo Dylint -- all. And what this will do is it will download all the lints in the lint subdirectory from the Solana lints repository. It will build them, and it will then run those lints on your project. I just want to mention that all of the hard work done in what I just talked about is actually due to these 2 gentlemen, Victor Way, who is currently a senior at Truman State University, and Andrew Haberland, who is currently a first-year PhD student at Carnegie Mellon. And I'll leave you with some links in case you want to learn more about the Solana lints, about Dylint itself, or the sea level attacks. And with that, I will happily take any questions.